feel free to ask them. And we'll start with that question, which is a good question. So remember that part of chapter 4 was really that intermolecular forces. And again, it's that recorded lecture. So if you haven't watched it, make sure you do watch it because it is part of the exam. So let's talk about really what was discussed sort of in that lecture. And that is intermolecular forces. So as we talked about there, there's really two types of forces. One's what's referred to as an intramolecular force. And intramolecular force really does mean within an actual molecule. So this is the force that holds one individual molecule together. So for example, if we took like an NH3 molecule, intramolecular forces would be all these individual nitrogen-hydrogen bonds, all the covalent bonds basically are intramolecular forces. If we talk about something like sodium chloride, which is basically Na plus and Cl minus, that attraction force between those two guys that holds one sodium chloride molecule together is an intramolecular force. And as I mentioned in that lecture and also that a little bit today, intramolecular forces are always weak, are always stronger. So these are really the strongest type forces. And they're definitely stronger than intermolecular forces. Intermolecular forces are the forces that hold two different molecules, or two molecules together. I won't say different because it can't be the same. Two molecules together. So that's what happens when you get, say, two NH3 molecules coming together. It is the bond that holds this entire molecule together with another entire molecule together. So that's an intermolecular force. So as I mentioned before, and as we talked about today with water, intermolecular forces are much weaker than intramolecular forces. And that's the same things you have with water, for example. When those two waters come together, they bond this way. And this is an intermolecular force, the force that holds this water molecule together with this water molecule here. And they're weaker because as we heat it, something like water, this bond right here breaks, and we end up getting two individual water molecules that occur. If the opposite was true and the intramolecular force was weaker, when we would heat something like water, we get like alphabet soup. All the elements would fall apart, and we get hydrogen gas and oxygen gas form. And that doesn't happen. Obviously, if you heated a pot of water before, you don't get hydrogen gas or oxygen gas that's formed. You basically get steam or water because we're breaking this weaker intermolecular force. So when we talk about intermolecular force, there's really three different types. There is what is referred to as dispersion forces. And dispersion forces are weak forces, really temporary type forces that really hold nonpolar molecules together with another nonpolar molecule. And ultimately, all intermolecular forces are really this interaction. It's the positive negative interaction. Those opposites attract is ultimately what all intermolecular forces really are. And when we do have something that's nonpolar, if you remember from bonding, nonpolar means that we have equal sharing of electrons. So equal sharing of electrons in a nonpolar molecule and this nonpolar molecule What that essentially means is there is no charge in either one of these molecules because the electrons as a whole are being shared equally. But what can happen in a dispersion force is because the electrons are flying around, it is possible that all the electrons in this, we'll call nonpolar molecule A here, in nonpolar molecule A, all the electrons will decide we're all just going to kind of go vacation on the right-hand side of this molecule, just for whatever reason. They're flying around, they all decide to go to the right-hand side. What that's going to happen is in nonpolar molecule A, which normally does not have a charge, it will temporarily gain a charge. Nonpolar molecule A. And if this nonpolar molecule A is still next to our nonpolar molecule over here, which is B, that also doesn't have a charge, when this guy gains a temporary charge, the negative side over here is going to make the electrons in this guy decide we want to get away from him. And they're going to go to the opposite side in that molecule. And now we have this normally nonpolar guy that doesn't have a charge, gaining a charge. And now this second guy that normally doesn't have a charge will gain a charge because its electrons also moved around, nonpolar molecule B. And now what we have is a way for these two guys that normally does not have a charge to have a way to interact with each other. And they can interact with each other through the positive side of one molecule and the negative side of another. And these are temporary and weak forces because at some point what's going to happen is the electrons, for example, in A are going to decide, I want to go back now. And it's going to go back to having really no charge. And then this guy will perhaps do the same thing and make another charge and a new interaction. So in dispersion forces, it is the main type of force for when two nonpolar molecules get together. And that's because they normally don't have a charge, but something happens that gives them a temporary charge. And that gives them a temporary way to interact with each other. But it's temporary because those electrons can move away. They're going to break apart those interactions and form new ones, break apart, form new ones, and break apart. And this is why these guys are basically relatively weak type intermolecular forces. And that is different than when we talk about dipole interaction. Dipole is also an intermolecular force. This is the force that is between two polar molecules when they get together. And dipole comes from something being a polar molecule. What that means when it is a polar molecule is it has a positive side and a negative side due to unequal sharing of electrons. Now, the difference between this positive guy and negative guy and the previous one is no matter what the situation is, he will always have a positive side and a negative side. He is good to go. He is ready to go right off the bat. Nothing will happen that will ever make his electrons go one way or the other. They're always going to be in that location. And that means that when two polar molecules get together, they both have a positive and negative side. And that's going to allow two polar molecules to interact through the negative side of one and the positive side of another. And we'll get that intermolecular force right there between those two. And this is a relatively strong interaction. And it's strong because they have what is referred to as a fixed dipole. They always have a positive and negative side. They don't have to wait for something to happen to get a positive and negative side like our nonpolar molecules. Like I said, they're pretty much good to go right out of the box, and they're able to interact with each other right out of the box. And nothing will affect that distribution of electrons. They will always have the same sort of distribution. So they're always good to basically come together. So if you had something like, this guy here, which is a polar molecule, and this guy, which is a polar molecule. they will able to interact this way where this side would be more negative, the carbon would be more positive. They would be able to interact this way. And again, this would be dipole-dipole interaction. Again, a relatively strong sort of intermolecular force. Now, the strongest of all the intermolecular force is what is known as hydrogen bonding. And it really is a dipole-dipole interaction, but it is a special type of dipole-dipole, and it really is the strongest out of all three of those. And it is involving a bond between hydrogen and an electronegative atom, like nitrogen, oxygen, or fluorine. So what happens in a case like this is the same thing. They have the ability to hydrogen bond. So water is an example of that. We have in water, water is a polar molecule where the oxygen is more negative, hydrogen is more positive. This is a bond between hydrogen and oxygen. This is able to hydrogen bond because of that. And when another water molecule comes near, also has a negative side by the oxygen, positive side by the hydrogen, they are able to interact with each other through the negative oxygen in one, positive hydrogen in another. This is what is known as a hydrogen bond here. And this is a really strong type because nitrogen, oxygen, and fluorine are the most electronegative, which means when you have the hydrogen involved, it will be very much a polar bond, and we'll have a pretty big separation of the positive side and negative side, which makes for a much stronger sort of interaction. Same idea here if you had something like this. And say water. Water again being negative there, positive there. This guy being negative, this guy being positive, able to hydrogen bond right there between those two. NH3 can do it as well. NH3 is polar. And it is more, excuse me, more negative here, more positive here. So two NH3s, for example, can do some hydrogen bonding between the, we'll go this way, hydrogen in one, nitrogen in the other, able to do that. Just because something has hydrogens doesn't mean it can hydrogen bond, though. If you had something like CH4, there is a ton of hydrogens there. But this molecule is nonpolar overall. And that bond between carbon and hydrogen is nonpolar. So even though this guy's got 4 hydrogens available to him, it cannot do hydrogen bonding because carbon and hydrogen is not oxygen and hydrogen, nitrogen and hydrogen, fluorine and hydrogen. It cannot do any type of hydrogen bonding. So because this really is a nonpolar molecule, this guy here would have to do some type of dispersion force. So out of those 3, hydrogen bonding is the strongest, and it is the intermolecular force that is used for polar molecules that have the ability to hydrogen bond. The next strongest is dipole-dipole, and that is for polar molecules that do not have the ability to hydrogen bond. And the weakest out of all of them are dispersion forces, and those are for really nonpolar molecules that obviously can only interact that way. The strength of something like a dispersion force increases with size. The bigger the molecule is, the bigger the nonpolar molecule is, the more electrons it can have. The more electrons, the greater the chance that it could create that temporary type of attraction. So when you're talking about sort of the strength of dispersion forces between 2 nonpolar molecules, it does increase with size because, again, more size, more electrons, greater opportunity for interaction to occur. Question on intermolecular forces there, while I read some of these things. Okay. Any questions on the intermolecular forces then? Okay. So again, if you were asked what would be the intermolecular force for this guy, hydrogen bonding would be his source. Even though he has a nonpolar part, this is the part that can do the hydrogen bonding. Yeah, you could do 4 different PDF files is fine. Again, just not like 4,000 pages though. Yeah, if you could. So the minimum amount of pages in terms of the homework would be appreciated. Minimum amount of files would be appreciated. But if you can't get them all obviously into one file, it might be kind of a big file. You could spread them up maybe by chapter is fine. But as long as I don't have like, 400 different pages of sort of uploads would be great. So any questions on that intermolecular force? Let me answer another question, which was about activation energy. So activation energy is the minimum amount of energy needed for a reaction to occur. And basically when a reaction occurs, when we go from reactants to products, what's going to happen is basically we're going to break all of these bonds and we're going to make new bonds on this side. And when we look at an energy diagram, which was also sort of in that chapter, energy, we have reactants, for example. Just do something like that. And our products here. So this is sort of an energy sort of diagram here. This is the reaction that's happening in this direction. And we could recognize this first off energy diagram as basically the exothermic reaction. And we know it's exothermic because our reactants are higher in energy than our products. So whenever your reactants, which is your starting material, are higher in energy than your products, this is going to be an exothermic reaction, which means heat and energy has to be given off. Easy way to kind of think about it is reactants are higher in energy. In order for them to get down to where the products are, it has to give off that energy basically to do so. But no matter whether it's an exothermic reaction like this one or an endothermic diagram, which looks something like this, and again, this would be endothermic because reactants are lower in energy than products, which would be endothermic. And that means same idea. If you think about the reactants, you got to put energy in to get to the products. But regardless if it's an endothermic reaction or an exothermic reaction, both diagrams, you could kind of see this hill right here. This hill from where the reactants are to sort of the peak of the hill there, that is what is known as the activation energy. And that's sometimes abbreviated E of A, which is activation energy. And it's basically the hill that the reactants has to climb to get to the other side to form products. And when a reaction takes place, basically two things have to happen. The molecules have to collide with each other, and they need to collide with each other with enough energy basically to start breaking those bonds and starting to make new bonds. And that's really what the activation energy is. It's that energy barrier that the reactants has to climb to get to the other side. If you look at the endothermic one here and this really badly drawn one, this would be the activation energy here. And you can see because this is an exothermic reaction, its activation energy is actually a lot lower than a endothermic reaction, because in an endothermic reaction, you got to throw some energy in there to help everybody get up and over to the other side. So really what the definition of activation energy is the minimum amount of energy that's required for a reaction to take place. It's thought of as the hill to get to the other side. And it affects things like how fast a reaction occurs. So the bigger the hill to get to the other side, the slower the reaction will take place. The lower the hill, the faster the reaction will take place because everybody can get to the other side. So for a reaction to occur, they do need to hit each other, and they need to hit each other with the right amount of energy. Not all collisions will actually make products. So just because two things hit each other, they may hit each other in the wrong orientation. They may also hit each other with not enough energy really to kick off basically that reaction from happening. So for example, in this, say a reaction like this, say you started with A and B over here. So we'll say A and B were like AA and BB, right? Were the two reactants. So when this reaction takes place, they're going to collide with each other. And as they're colliding and kind of working their way up this hill, what's happening is the bond between A and A is breaking, and A is forming a new bond between, say, B and B, right? This other A is coming over here and kind of forming a new bond. So as these guys come together, they hit each other, they have enough energy to kind of reach them up over the hill. And as they get to the top, they're starting to break some of these bonds, and they're starting to make some new bonds. So that when they get to the very top, they usually will drop down very quick to the other side and make their products, which are, say, our new guys that are formed over here. So ultimately what sort of the activation energy is just that. It's really sort of thought of as an energy barrier from the reactants going to the products that needs to be met in order for a reaction actually to take place. Again, if those guys, as they hit each other, don't have that minimum energy, which is that activation energy, no products will be formed as a result of that reaction. So sometimes people think all you need to do is have two things basically run into each other. But that's not really the case. Even if they run into each other with the right amount of energy, they actually need to run into each other in sort of the right location, like the active side of each of those guys, to allow products to be formed. So just some to hit each other doesn't necessarily mean that products will be formed. One of the factors to allow products to be formed is they have to clear that hill to get to the other side, and that hill in terms of energy to do that. Any questions on activation energy? I look at the questions here. Okay, you're welcome. Let's see. Got that one. Resonance, Vesper, and polarity. Okay, so so resonance structures in general are when you have really the chance to draw, or you can draw more than one Lewis structure for a particular molecule, and that's because there's sort of choices where you could double bond something. So for example, let's do we'll look at carbonate again, maybe. So if we look at carbonate and we want to draw the Lewis structure for it, we would go carbon is group 4, so it's 4 valence electrons. Oxygen is group 6, and there's 3 of them, so there's 6 times 3. And again, the -2 here means we do need to add 2 electrons because it gained 2 electrons. And that gives you 18, 20, 24 electrons. So remember, when we draw a Lewis structure, least electronegative in the center, other guys on the outside. We want to do one single bond to everybody. That's going to give us 2, 4, 6 electrons. Rest will go on the outside in pairs. So that's going to be 8, 10, 12, 14, 16, 18, 20, 22, and 24. We have now used all 24 electrons. Remember that we want to make sure everybody has 8. So the oxygens on the outside, 2, 4, 6, 8, they're all the same. Carbon on the inside has only 2, 4, and 6 electrons. So remember that you do want 8, except for hydrogen that should only have 2, only, basically 1 bond. So in this case, we do need to make a double bond to try to fix it. And because all 3 of these oxygens are exactly the same, we can make the double bond really at any one of these oxygens. When we go to make a double bond, as we talked about, you do need to take a pair of electrons, so I'm going to take the top ones, and erase them, and then bring them in to make that double bond. Otherwise, you will end up with too many electrons. So I'm going to erase those electrons. I'm going to make my double bond here, and that would give me 1 Lewis structure for carbonate. Now, I could have just as easily brought my electron pair in for the guy on the right. And if I did that, I would get a structure that is the exact equivalent to it. It will look just like this, except that the double bond would be over here on the right-hand side. And this would also give me a and I actually had a third option, which is I could double bond on the left-hand side. And if I double bonded on the left-hand side, it would look like this. Basically just moving that double bond from all the possible locations. And this would give me a third structure. And all 3 of these structures are related to each other as what are referred to as resonance structure. And that is because these double bond electrons are what are referred to as being delocalized, which essentially means that at any given point in time, those 2 electrons that we brought in to make these double bonds could find themselves at any of the oxygens, which means at a certain period of time, it may be hanging out over here at the oxygen on the left, or it may be hanging out over here at the oxygen up on top, or maybe hanging out over there at the oxygen on the other side. And those double bond electrons are basically moving around the entire molecule, which means we could draw 3 structures, and the real structure is probably somewhere between all 3 of them. And you wouldn't necessarily have to draw all 3 of these unless it asks you to do so. You could have drew any one of those guys and it would have been perfectly fine. So that's basically what resonance structure is. Again, if we look at, say, SO2, which looks something like this. When I'm drawing SO2, I could have ended up double bonding here on the right. I could have also, if I wanted to, did the double bond on the left-hand side, and it would look like this. And these 2 guys are resonance structures of each other. Again, really the easy way to think about it is if you have more than one option as to where you could put that double bond, you could draw another structure for it. Any questions on that? Now, the other question was about sort of geometry. So when we look at something, say, like our carbonate, and when we're doing geometry, remember that the really main rule is if you have a double bond or a triple bond, it only counts as 1 electron pair and 1 bond. So when we would look at something like carbonate here, we want to go always to the center atom is the important one. So it would have 1 electron pair here, 2 electron pairs here, and even though it's a double bond, this would only count as 1 electron pair. So this guy would have 3 electron pairs. Now, when we're counting bonds, we do the exact same thing. Double bonds, triple bonds count as only 1 bond as well. So when we look at this central atom, 1 bond here, 2 bonds here, and 3 bonds here, which would be 3 bonds. Now, we talked about 2 different types of names, but for the exam, you only need to know the molecular geometry name. But we talked about the electron pair geometry. And electron pair geometry is based on how many electron pairs there are, which is 3. So this would be known as trigonal planar. And because these are all bonding electrons, no dots on the central atom, the molecular geometry name, or the shape, would also be the same name. It would be trigonal planar. It basically makes a triangle type shape if you sort of draw it like that, or triangular type of shape. Now, if we look at something, say, over here at this guy, again, if we were going to do geometry, we want to look at the central atom. And if we counted electron pairs, this would be one electron pair. I'll just make a big dot here. These two dots up here were one more electron pair, and this double bond would count as just one electron pair. So again, that is 3 electron pairs in this case. In terms of bonds, what we have on this one is one bond here. And again, double bond only counts as 2 bonds. So when we do something like electron pair geometry, it has 3 electron pairs, which is still trigonal planar. But we have 2 bonds and 1 electron pair, non-bonding electron. So that's going to give us a molecular geometry of angular in this particular case. So when you're trying to do sort of geometry, and really for us, we're only really going to focus on for lecture the molecular geometry, or the shape. What you really want to look at is always the center atom. And what you want to look at is the number of electron pairs. Doesn't matter if they're dots, doesn't matter if they're lines, and the number of bonds, which would be just the lines. So something with 2 electron pairs and 2 bonds is linear in terms of its molecular geometry. Something with 3 electron pairs and 3 bonds is trigonal planar. Something with 4 electron pairs and 4 bonds is tetrahedral in terms of the shape. Something with 4 electron pairs and 3 bonds is trigonal pyramidal or pyramid. 4 electron pairs, 2 bonds is bent or V-shaped. And the one we just did, 3 electron pairs and 2 bonds, is angular. So that is definitely what you want to sort of count and look at. Remember that if you have a diatomic molecule, which is basically just 2 atoms, the geometry is always linear, so you don't have to worry about it. It could be 2 atoms that are the same element, 2 atoms that are different elements. Geometry will always be linear when you have just a diatomic molecule. And the last part of that question, I think, had to do with polarity and molecular polarity. So when we talk about sort of molecular polarity, if we have a diatomic molecule, it's pretty easy because they only have 1 bond. So if you have F2, doesn't really matter, N2, whatever it may be, O2. All 3 of these guys all have only 1 bond total in the entire molecule. And in each of these bonds, these are all nonpolar bonds because they're the same element, which means their electronegativity values will be the same. And they should share the electrons the same. And because these are all nonpolar bonds, and because in each of these, there basically is only 1 bond, that means that the molecule would be a nonpolar molecule as well, as a whole. And the same thing if you had 2 different guys like HF, HCl, something of this nature. When these 2 guys, each of these guys have polar bonds based on electronegativity values heading towards the fluorine or the chlorine here. And they all have polar bonds. And because there is only 1 bond in the entire molecule, each of these will have to be polar molecules. And again, If you have a diatomic molecule, easy to figure out if the overall thing is polar or nonpolar because it only has one bond. If that bond is polar, the entire thing is polar. If that bond is nonpolar, the entire thing is going to be a nonpolar molecule. It gets more difficult when you have 3 or more atoms. When you have 3 or more atoms, you have to look at, are there polar bonds? And if there are polar bonds, what you have to look at is the molecular geometry. So we talked about how you could kind of do it and that these little lines are vectors and all that. But we also talked about basically that there are symmetrical geometries. And symmetrical geometries are essentially your trigonal planar, your tetrahedral. And what all these have in common, these two guys, is when you draw your Lewis structure, there are no non-bonding electrons. On the central atom. So if you draw your Lewis structure and you look at your central guy and you didn't put any, it's going to most likely be one of these geometries for us. And that's going to be a symmetrical geometry. And if everything attached is the same element, the molecule will most likely be nonpolar. It would be a nonpolar molecule. So for example, if you took CBr4, right, and we drew it out. I won't draw the dots on the Br, but there's dots all around them. When we draw this Lewis structure, I look at the central atom, no dots. Everything on the outside is exactly the same element. This is going to be a nonpolar molecule. And that's because they're basically going to be equal and opposites of each other. So as they pull, they're going to pull equal and opposites of each other like on a rope. So if everybody pulls equal and opposites of each other on a rope, the rope's not going to move anywhere and they'll cancel each other out. So this will be a nonpolar molecule. But if we took one of these guys and swapped them out for, say, a hydrogen, and if we took that same guy and instead of having 4 of these BRs, but put a hydrogen on there, what's going to happen is bromine is more electronegative than carbon. So they're going to pull, we got 3 guys pulling in this direction, and this carbon-hydrogen bond is nonpolar, which means it's not pulling in the opposite direction. If anything, it's actually pushing with them. So we're going to get kind of like a net movement happening in this direction, and this will now become a polar molecule. So if you have trigonal planar or tetrahedral, and everything on the outside is the same element, going to be nonpolar. If you have those geometries and you change one of the guys on the outside and they're not all the same element, I'll say there's a 90% chance, maybe 92% chance that it is going to probably be a polar molecule in that case. And that leaves us really unsymmetrical geometries. Unsymmetrical geometries are your angular, your trigonal pyramid, your bent or V-shaped. And what all these guys have in common is if you draw your Lewis structure, your center atom has non-bonding electrons, basically dots. Yeah? And if you have that situation and all the elements on the outside are the same, it will most likely be a polar molecule. So like this, NF3. I won't draw all the dots on the fluorine. I look at the central atom. I see dots. I see everybody the same. This is going to be a polar molecule. And that is probably the best way to sort of do it, is in that sort of sense. Most people can't visualize sort of three-dimensional and pulling. So for example, you could do it really quickly, like we had this guy. We had, say, this guy. We had like this guy here. I won't draw all the electrons. Let's do this guy. Let's do, that looks good, I guess, for now. We'll talk about this guy as well here. All right, so if we look at these guys, again, literally you could jam through these guys pretty quickly. This is how I would approach it if I was looking at to try to determine polar or nonpolar. As a molecular polarity, I would go to the central atom. I see dots. I see everything the same. That is going to be polar. That's an unsymmetrical guy. I see central atom. I see no dots. I see everybody's the same. That's going to be a nonpolar molecule, even though carbon hydrogen is nonpolar to begin with. So that should also help you. I go to the central atom. I see no dots. I see everybody's the same. Going to be nonpolar. I go to central atom. I see dots. I see everybody the same. Going to be a polar molecule. I go central atom. I don't see dots, but I see polar bonds. But this guy is linear. This geometry is 2 electron pairs and 2 bonds. And in a straight line, we've got one guy pulling this way, one guy pulling the other way. They are going to cancel each other out. And this is going to be nonpolar, this guy. I go something like this. I see no dots on the central atom. I see everything on the outside is not the same. This is going to be a polar molecule. So that's a much easier way to sort of look at it, as sort of symmetrical and unsymmetrical geometries, which really does leave you just linear as the one you have to worry about. And since linear is a straight line, if they're going equal and opposite, it's going to be nonpolar. If they're both heading exactly at each other, it's going to be nonpolar. But if they're all heading in the same direction, it would be polar as well. Question on that. I think that was all that there. All right, let's see, units of energy. Let's see here. Units of energy. Really, there's joules, which are J. There's little calories with little c, which is our calories. And you're welcome. And the relationship between this is there's 4.184 joules equals 1 calorie. And also kilojoules are kilocalories, which is 1,000 joules, or 1,000 of the little calories. There's also nutritional calories, which is a capital C here, and that is equal to 1 kilocalorie, which is equal to 1,000 of the little, not joules, I'm sorry, 1,000 little calories there. And a capital C is sometimes, again, a nutritional calorie. And I think in the lecture, I did an example where we had caloric values. And that's where I used, for example, fat is 9 kilocalories per gram. Carbs are 4 kilocalories per gram. And protein is 4 kilocalories per gram. That's how they get the calories on like your nutrition labels, by doing those type of things. So I think that's mainly what we talked about on that. We did also talk about specific heat, our specific heat capacity, and I won't worry too much about that. Specific heat capacity. And that's basically the energy needed to raise 1 gram of a substance by 1 degree Celsius. And those are the guys that have the units of joules per gram per degree Celsius. And basically, the higher the specific heat capacity, the more energy it takes to change the temperature of that substance. So if you had something like water, which has a specific heat capacity of 4.184 joules per gram per degree Celsius, that is much higher than, say, a metal that has 0.155 joules per gram per degree Celsius. It would take less energy to change the temperature of this metal by 1 degree Celsius than it would here to change water. And again, that's why, when we change, say, water overall in our sort of world by a little bit of a degree, it's a big issue because it takes a lot of energy just to change that little bit of water by 1 degree Celsius. Question on that there. Other questions I could help you with? Okay. If you have questions, feel free to hang out. I think we're towards the end here of discussion. So I'm good if you're good. Have a good rest of your evening. If you still have questions, I'll be happy to answer them. Otherwise, again, remember that the exam is on Wednesday. There will not be lecture. Again, you'll have a module to finish, and you do need to start at the beginning of lecture. Otherwise, you will run out of time. It will not be reopened for you or extended for you. So make sure you start at the beginning of lecture, and you should be able to get all the time that's allotted to you. Again, if you start later, you'll get less time. So you're expected to start around the start of lecture. Any questions on anything? I'll do my best to get it up there before Wednesday. Other questions?